So, Chapter 3, Location Inference for Single Samples. We will have 2 lecture videos for Chapter 3. Both videos are posted in this week. And this is the first video. It's about section 3.1 to section 3.3, from slide 1 to slide 36 of our presentation slides. And then the second video will be posted either late Thursday or Friday morning. Anyway, it will be ready on D2L by Friday noon Mountain Time. So it's about the rest of the sections of the Chapter 3. And then in that video, I will give some feedback of homework 1. So I try to make multiple short videos instead of one long video because I may feel boring and get lost if the video lecture is too long. So the audience will be even more bored and get tedious, right? So for this week, all the videos will be posted on D2L by Friday noon, but I know it's a little bit late. So then from next week, I will make sure all the videos will be ready by Thursday noon if it has multiple videos. If it's only one single video, then it will be ready on Wednesday. So then for this week, the first video will be a little longer than the second one. So you may watch them back to back after the second video being posted. And I try to make the lecture videos in each week totaling less than 2 hours. If it's more than 2 hours, then you use speed 1.5. And please do not rely too much on our presentation and also slides. You still need to spend some time to read the textbook, especially for the specific examples and sections that I invite you to read. So let's begin Chapter 3. So first of all, when we talk about some problem, there will be some specific topics we need to know. And those are the topics. This is the layout for all the examples in this chapter. We first introduce the problem, the data, the context, then formulate the problem and make assumptions. So the formulation is usually formulating a hypothesis test, and assumptions are usually whether the data is asymmetric or not. And then we go through the procedure of our hypothesis testing, and with the testing results, we make some conclusions and comments on our data, on our method, in the context of the problem, whether we need a larger sample study, and so on. And then we talk about the computational aspects regarding some software, some packages. And then as to the fields of application of each method, we will summarize them by the end of this chapter. So first, the requirements or the assumptions of the data samples we use in this chapter. So the data are all continuous, which means the observations can be any value in a range. Although maybe sometimes they are integer, they can be any integer in a range. And although there are 2 or more sample studies in this chapter, we first start with the single sample problems because they are useful on their own. The methods for 2 or more sample problems are extensions of the single sample methods we introduce in this chapter. And single sample methods can also deal with some real-world complications, such as the tied data values, censored observations, and outliers. And then something about p-value. We have a notion as exact p-value, which means using the sample data with each observation given a value, and we consider that value, the order of that value in terms of our sample data, and using that order to calculate the exact p-value. That's for the small data sets, right? Because if the sample is too large, it's not easy to calculate the exact p-value. If that's the case, we use asymptotic results. Because when our sample is large, it may approach to normal distribution or some other distribution. Then we will have that distribution as an approximation of our sample data. Therefore, we use some lookup table such as the standard normal distribution lookup table, the Z table, to help us determine the p-value, the asymptotic p-value. Right. And another way is Monte Carlo solutions. We can generate data and use those data to get p-values. So given those are our assumptions that we use continuous single sample and we use order statistics or ranks instead of the complete measurements or real observations. So let's look at a method to get inferences about medians based on ranks. Wilcoxon signed rank test. We hypothesize a median value theta 0 for n observations. For a process based on this n observations. But the parameter being tested is not the median, but the deviation of each measurement versus the theta 0. So we first convert the observations xi's into deviations di's. How to convert it? Simply use the xi to subtract theta 0, right? So this deviation can be negative or positive, right? So the deviations are with signs, which means if a deviation is a positive value, then its sign is positive. It means this observation is larger than the theta 0, right? And vice versa. Then we use the sum signed ranks S to obtain the p-value and make decisions on our null hypothesis. Let's go through the procedure step by step and then look at an example to get familiar with the method. So first, the problem. Suppose we have an observation in a sample of a process, and then test if the median of the process equals theta 0. Suppose this is a two-sided test. Next, formulation and assumption. We use DI to denote the deviation, the difference between the ith observation and theta 0. We also name deviation as magnitude. By the way, in basic statistics, we have learned that if a data set is symmetrically distributed, its median should be equal to its mean, right? Then the testing procedure. Calculate the magnitude of deviation of each observation from theta 0. In other words, we use xi to subtract theta 0 to get di, and di can be negative and positive. And magnitude is sometimes when we say magnitude, it means the absolute value of di. So magnitude will be always a non-negative value. Then order the magnitude or absolute value of DEI in ascending order. And these are the ranks. Then we give each rank a sign, a negative sign or the positive sign, the same with the corresponding deviations. And these are the signed ranks. Then, under the null hypothesis, if the sum of the positive ranks, and we denote it as S plus like this, if the sum of positive ranks is much higher than the sum of negative ranks, then theta 0 is unlikely to be the population median, right? And vice versa. So once the sample size is given, we can get all the sum of positive and negative ranked signed ranks, right? Because we only care about the ranks. And when the sample size is given, then all the possible values of the S plus and S minus and their probabilities would be fixed. So then in the extreme case, when all observations are larger than theta 0, then the sum of negative sign ranks should be 0, right? Because all the observations are larger than theta 0. The S plus would be at its maximum value. For a sample size 7, it will be 28. And on the contrary, another extreme case, if its theta 0 is too large, all the observations are smaller than it, then S plus should be 0 and S minus would be 28. So any case in between, the sum of S plus and S minus would be 28, right? So we know that all the signs and their probabilities, sign values and their signed rank values and the probabilities are determined by the sample size. And when sample size is n is 7, then signs may be allocated to ranks in 2 to the power of 7, which is 128. So there are 128 ways of allocation of the assigned ranks. And the distribution of S plus depends only on the sample size. If sample size is 7, then S plus can be any integer between 0 and 7. And the distribution should be symmetric, right? Is more likely to get, it has a higher chance to get the value in the middle, but lower chance in the upper and lower tail. So if that's the case, 128 is not a lot. Therefore, we can use a table like this to illustrate all the S value, S plus and S minus value. This is table 3.1 in our textbook. So we use K to represent the value of S plus or S minus. And S plus equals 28, subtract S minus, right? And this is a symmetric distribution, about 14.5. So let's look at how we get those probability. For example, when S plus equals to a certain value, there may be one or multiple scenarios of the ranks, the signed ranks, to get this K value. For example, if S plus equals 4, for this case, then there are 2 scenarios of signed ranks to have a sum as 4. One is rank 1 is positive and rank 3 is positive, and all the other 5 ranks are negative. So S plus would be 4. And another scenario is only one rank is positive, that is rank number 4, right? Only the 4th rank is positive and all the other 6 ranks are negative. We can also get S plus as 4. So let's look at another example. When S plus equals 9, there are 6 scenarios. Rank 2 and 7 are positive. Rank 3 and 6 are positive. Then rank 4 and 5 are positive. Then rank 1 to 6 are positive. And we saw some 1 to 6, that's 9. And then another scenario is rank 1, 3, 5 are positive. Then the sum of 1, 3, 5 are 9, right? And then the last one is rank 2, 3, 4 are positive, and all the other 4 ranks are negative. The S plus will be also 9. So those are the 6 scenarios. So the probability is 6 over 128. And the symmetric thing is when S plus equals 9, and then 28 subtract 9 is 19. So when S plus equals 19, we will get the same probability, right? So given that, let's look at an example with a 7 observation sample. So the heartbeat rate, the heart rate, which means the ppm, the BPM, beats per minute, for a 7-member group are given here. Those are their heart rates. So n is 7. Test if the median of the heart rate of all humans is 70. And the alternative is theta is larger than 70. So it's a one-sided test. Next, formulation and assumptions. We hypothesize that the sample is symmetric or near symmetric, scatter about 70. So the alternative hypothesis implies S plus may be larger than S minus, right? So next, the procedure of getting the test statistic and p-value. So we know that we use S plus or S minus as a test statistic. So how do we get that? We use each observation xi, which are given on slide 11, xi to subtract theta 0, which is 70 in our case, to get di, and those are given here. Then, based on di's, we get the signed ranks here, right? So with the signed ranks, we can calculate the S plus and S minus. So for this case, for any case, we just need to calculate one, right? Because the other one is simply using the total number of values. For this case, is 28. To subtract the S plus, we get S minus. So for this case, we only calculate S plus. That is 24. And then, because the critical region is the upper tail, we need to know the probability of S plus reaching 24 or above that. Therefore, we go back to table 3.1 to see that that's the probability, cumulative probability of these case. So when we add them, that is 7 over 128. And that's the p-value, exact p-value, 0.055. So, conclusion, the p-value in this case is not strongly against the null hypothesis. If it's very small, much smaller than 0.05, then the p-value is strong against the null hypothesis, right? This one is not. So, which means we may need a larger sample to find a stronger evidence, either support or against the null hypothesis. Comments. The p-value is a result of a small sample, right? So we can make more confident discussions on the null hypothesis. And this is a one-sided test. If it is a two-sided test, then we just need to double the p-value. Because in that case, we care about two critical regions on the lower corner, lower tail, and upper tail. And if it's symmetric, then we just need to double the p-value. So we may use S plus or S minus. For this one-sided problem, if we use S minus, then we need to use 1 to subtract the sum probability, right? Because the alternative is care about the upper tail. Therefore, when we calculate S plus, we directly use that cumulative probability. But when we use S minus, we need to use 1 to subtract that probability to get the p-value. Okay, so when using classic parametric test, when p is less than the significance value, 0.05, as the value we regularly use as a significance level, then we reject the null. But for small sample non-parametric problem, we fail to reject the null when p-value is less than 0.05, especially when p-value is slightly less than that, because the sample size is small and p-values are not quite continuous. As the sum of the sign ranks S plus varies vary a little bit, then p-values vary a lot. It simply jump from 0.01 maybe to 0.05, and there's no information in between. So a small p-value is not strong evidence against the null. Regarding the computational aspects for this problem, because the sample size is small, we can use the lookup table, table 3.1, and list by listing all the S plus and S minus value and their probability to calculate the exact p-value, right? But for a large sample, we have to use some computer packages and software to help us calculate the p-value. In our textbook, they usually use StatExact and Minitab. So Minitab, I find there is free education version or a 30-day free trial. So just use your ICMinds student email, you can access Minitab. But for StatExact, I didn't find any free version. So we, for this course, we require R, and StatExact is not required, but we only talk about their differences. So for this problem, for R, we use this P sign rank to get the p-value. The first value is the value next below the S plus, or the value that we involve into the non-critical region. And then the next number is the sample size. And then lower tail equals if it's false, which means the alternative is about upper tail. And if it's true, then it means the alternative is theta less than some value. So let's go to R Studio. So I bet you all know that, but in case some of you forget how to use R, we simply download the free version from our official website. Then, personally, I prefer RStudio, but it is not required. So for RStudio, I use Anaconda to launch it. After downloading R, installing it, then I install RStudio from here. After installing it, so my version is an old version, but it doesn't matter so far. And then you click launch here, then you can get to the RStudio and use the console here, this window, to operate. So for our problem, we need to calculate the largest S plus that is in the non-critical region. So which means our S plus is 24. And for R, we need to use 23. And then define the sample size 7, lower tail as false. Then we get this R value, sorry, P value. So let's continue. Then if we do not use computer programs, then even with a small sample size, manual calculation of probabilities for all values of S plus or S minus can be done. But it's a very time-consuming and tedious job, and you may make a lot of mistakes. So as the sample size n increases, the computational complexity dramatically increases. So if n equals to 12, then there are this much, 2 to the power of 12, that is 4,096 possible allocations of signs with ranks. So for a symmetric distribution, S plus can be any integer between 0 to 39. So for each value of S plus, there can be one or multiple signed ranks scenarios, right? And most of them are multiple scenarios. So that's a lot of work manually. So this is the table. Even with n equals 12, we can make such a table. But with a much larger n, it's not a wise idea to make such a table. So this is to list all the Wilcoxon signed rank statistics with their probability, right? But for each k value, we need to manually identify. If we make this table manually, we need to manually identify all the scenarios when S plus equals these values, then to identify the probability. And after identify all the probabilities, we need to sum the value up to see if it equals 0.5, right? Because this is symmetric distribution. We only list the half of them, and the other half are just symmetric with these. So the sum of all these probabilities should be 0.5. So this is the bar chart to illustrate the distribution of the Wilcoxon signed rank statistic in this table. So we call it bar chart instead of a histogram because each bar is the occurrence of one k value. So for histogram, we combine multiple observed values in one bin. So that's the difference. But histogram is belongs to the bar chart, right? So this is the difference. And you may observe this is symmetric, and moreover, it looks like it is a normal distribution, right? So when the sample is large enough, remember the central limit theorem, we may use normal distribution to approximate such data set. So let's leave that normal approximation for a while, and later we may use it to get the asymptotic result. So next, let's look at another example. Not let's look at, but you look at it. So I will skip this one. Please go through slides 19 to 23 to learn this example. If you need more details, go to textbook, section 331, example 3.2. Pay attention to the conclusion and comments of this example. Those are the insight, interpretations, and aims of doing this test. And in summary, hypothesis testing usually tells whether to reject a null hypothesis. But if the null is rejected, it tells nothing about what other hypothesis might be plausible, right? That's the limitation. We need to know that. But with that limitation, we can still perform the hypothesis testing, right? So next, let's jump to slide 24, section 332, to learn confidence interval based on signed ranks. To establish the confidence interval of median, we need to first introduce another statistic, Walsh averages. So Walsh averages are all the paired averages among the observations. We calculate the average of any two observations in the sample. Why do we need a new statistic to identify confidence interval? And why Walsh averages? Because for nonparametric problem, when sample size is small, by using the ranks p-values are not quite continuous, remember? So the confidence interval is also not quite continuous. If we only use ranks and the corresponding observed values, the upper and lower bounds of a confidence interval, or we should say the confidence limits, the confidence limits will only equal to two observed values, right? How about the values between two neighboring observations? So to explore the values between the neighboring observations, we need to develop a new statistic to help us reach to the values in between. And that is Walsh average. For an n observation sample, we can get half of n by n minus 1 Walsh averages, right? N multiplied by n plus 1 divided by 2. So that's the number of the Walsh averages, much larger than n, right? And in that way, we may have the confidence limits equal to a value other than the observed value, in between. So the Walsh averages have connections with Wilcoxon signed ranks. The connection is the number of Walsh averages less than or greater than the hypothesized median theta 0 is S minus or S plus, respectively. So in example 3.2, which we skip, if you have read it, p-value is slightly more than 0.05 if S plus or S minus is 14. So the 95% confidence interval should cover from 14th smallest to the 14th largest Wilcoxon signed ranks. And the confidence limits should be the 14th smallest Walsh average and the 14th largest Walsh average. So let's find them. Using example 3.2, we can list the Walsh averages in a matrix like this. The average of any two items will be in the middle, right? For example, average of the 4 and 8 is this. This is the 4, and this is the 8. 8. 8 and 4, yeah, here. 4 and 8 here. We omit the bottom left triangle because they are just the same, symmetric with the upper right triangle. When we transpose this kind of matrix, we get the same matrix. That's why we can omit half of them. And there are 87 Walsh averages here in this table, in this matrix. Y78, that is 12 multiplied 13 divided by 2, right? N by n plus 1 divided by 2. Then we can easily identify the 14th smallest Walsh average is here, 2.5. And all the items in this corner are within the range of the first 13 smallest. Anyway, this is the 14th smallest, and this is the 14th largest, 16. So the 95% confidence interval is from 2.5 to 16. In this way, the confidence limits can be a value not in the sample, right? Although 16 is a value in the sample, 2.5 is not. So in this way, we explore the values between the observed values. And in our textbook, we only focus on Walsh averages, but you may have observed that if you use more items, more observations to calculate averages, then the averages would be even smoother, and we may get more values in between to create the confidence intervals. Walsh averages are a good idea to do that. So let's continue with slide 26. the asymptotic results. So we know that for small and medium-sized samples, we may use software to perform exact permutation tests. If you forgot what permutation tests are, go back to section 2.1 or go back to our chapter 2 presentation from slide 3 to slide 7 to quickly review permutation test. Anyway, for small and medium-sized samples, we may use software to perform exact permutation tests. We do not need to use asymptotic results for such samples because the computational complexity is not too high. And only when the sample size is moderately large, the asymptotic results may be reliable. But how large is moderately large? It depends on the procedure being used. For example, for Wilcoxon signed rank test, when n is 12, the distribution of test stat S plus or S minus approaches normality. Remember the bar chart, right? The expected value of S or the sample mean of S. Here S can be S plus or S minus. So S mean of S can be 1/4 of this. Why is this? Because the sum of integers from 1 to n is 1/2 of n multiply n plus 1. So then 1/2 of the sum of magnitudes would be 1/4 of this, right? So when n is large enough to approach normality, we may convert the distribution of S into a standard normal distribution by using the test statistic S to subtract its mean divided by standard deviation. So this is a asymptotic result. Because the sample is large enough to approach normal distribution, then we use the normal distribution way to convert any S to a Z. Therefore, we can use the standard normal distribution lookup table, the Z table, to determine the probability of getting a certain value of S. All right. So let's look at a couple of examples to get a better understanding of this method. Okay, I almost skipped this part. This is important, the continuity correction. So what means continuity correction? So that is a way we improve the test statistic S. How do we do it? Since S can, and why do we do it? Since S can only be integers, we may approximate it to a continuous distribution by adding 0.5 to S plus if S plus is lower than S minus, or by subtract 0.5 from S plus if S plus is larger than S minus. Therefore, we make S from integer into a value with the decimals. Therefore, we make the S more continuously distributed. So let's look at an example. Example 3.4 in our textbook. We have 12 female students. When standing up from laying down, their heart rates change. Assuming their heart rate changes are symmetric about the median, and the hypothesized median is 15. We use two-sided alternative. Then we use the asymptotic approximation of Wilcoxon signed rank test, which means we need to calculate the Z value of our S and use the Z table to look up p-value. So how do we do it? For example 3.2, we know that when sample size is 12, it's large enough to approach normality, right? From that bar chart, we can see. So let's use a asymptotic result to calculate p-value. First, the test statistic S is used the corrected continuity correction because S plus equals 14, which is lower than S minus, right? Because S plus can be any value from 0 to 39. Then if the sum of them is just 14, then this is a low value versus S minus. Therefore, we use 14 to plus half as the corrected S plus. So that is 14.5. That is the test statistic. Then we use this equation to convert S into Z. So we first need to know the sample mean of S plus. That is, using the equation in the previous slide, we get 39. And the variance, use the equation from the previous slide, we get this value. So Z value is simply using S plus corrected to subtract mean divided by the standard deviation, which is negative 1.92. And using Z value and Z table, we get the p-value for negative 1.92, which is 0.55. So if we want to use software, we can also use the R to calculate this p-value. And since it's a two-sided test, we need to double it. So that is this value. With the asymptotic result, we can make conclusion and comments. P-value is again very close to 0.05. It is not evidence strongly against the null hypothesis. Since this p-value is very close to the exact p-value we calculated in example 3.2, we can conclude for n equals 12, the approximation looks very close. When we use the asymptotic result, it's the same, almost the same as the exact p-value. So being able to get probabilities for S plus and S minus allows us to get confidence intervals using Walsh averages. Not all the software applies the continuity correction. For example, StatExact does not, and Minitab use the continuity correction. So we talk about using Wilcoxon test when there are no ties in ranking. Now let's look at Wilcoxon with ties, which happens quite often in practice. For ranks with ties, the Wilcoxon dot test in R does not work. The p-sign test in R does not work either. If you use tied data, R gives you warning about it. But the StatExact in our textbook uses works just fine. For this part, we only focus how it works theoretically. If we won't require the hands-on experience of using StatExact. If you happen to have StatExact in your computer, you may try it, but we don't require it in this course. In this course, we mainly use R. So how the Wilcoxon test works if you have ranks with ties? Often we use mid-ranks. For example, for this sample with 7 items, a lot of ties, right? We want to test if the median equals 3. Then the sign rank, if we use mid-rank, sign rank, we get this. How do we get this? With these observations, then the deviations are -2, -2, 2, 2, 5, 5, 5, right? A lot of ties. So how do we rank them? using mid ranks. The first 4 deviations have the same magnitude, right? 2, which is 2. And their ranks should be from 1 to 4, right? So we use the mid of the 4 ranks, the average of 1, 2, 3, 4, which is 2.5. So, and we assign them with the signs as deviations. So the first 2 are negative 2.5. The next 2 are positive 2.5. The same case with the next 3. Because the next 3 should be ranked as 5, 6, 7, right? Then we use the mid ranks. Average of 5, 6, 7 is 6. So we all give them 6, and they are all positive. So the mid ranks are like this. Then we can use these statistics to proceed our hypothesis testing. Let's look at a couple of examples. Example 3.5. Why do we have ties? Sometimes it's a result from rounding, but we may encounter difficulties of interpretation with ties due to rounding, because different samples with different statistics can be rounded as the same sample of integers with ties. Just look at these 2 samples. They are different, right? But when we round them to integers, they all get this sample. But these 2 samples here, they may have different median. So these 2 samples are very different when we get their signed ranks. But when we round them as integer, as this one, they have the same signed ranks, right? So there's information loss and errors brought by rounding and ties. For the 2 original samples, for these 2 samples here, the signed ranks are here. There's sum of negative ranks as minus. For the first sample is 3. For the second sample is 7. Big difference. And for the first sample, when S minus equals 3, its p-value is 0.039. It's in the critical region. We should reject the null, right? The null is the median equals 3. But for the second sample, S minus is 7, and the probability is 0.148. And this is not in the critical region. We may not reject the null with this p-value. So if we use Wilcoxon with ties, and if the ties are due to rounding, our conclusions may be wrong. We may get different conclusions. So one more example, example 3.6. We got the number of words in the first sentences in 12 randomly selected paragraphs from Fisher's 1948 publication. So actually, I don't see any point of this data. Unlike the heart rate or heart rate changes, everybody knows the value of studying that data, right? But this one, the number of words in the first sentences, do not reflect the writing quality or anything, right? But anyway, let's use this example to show how to use Wilcoxon with ties. Given we have 12 measurements, and we want to test if their median is 30 or significantly larger than 30. Although this is a one-sided test, we assume symmetry again. Whether it's a one-sided or two-sided test, and whether the data is symmetric, those 2 things are independent with each other. If the median is not 30, the data is symmetric, then the data should be symmetric about another median value, right? So those are 2 independent things. So we use mid-ranks for ties. First, we calculate the deviation of each observation from 30. They are listed here. with signs. Then, with those deviations, we identify their signed ranks. If there are ties, we use mid-ranks to deal with them. For example, -12 and +12 have same magnitude, and their ranks should be from 5 to 6, but they are the same. Their magnitude are the same, so we use their mid-ranks 5.5 for both of them. So -12 sign rank is -5.5, and +12, its sign rank is +5.5. And the same story with the 2 19s. So using these mid ranks, we get the sum of negative sign ranks using one-sided or one-sided test, or we say one-tailed test. We can get the p-value with software, and because it's less than alpha, its p-value is this 0.04 something. It's less than alpha. We need to reject the null hypothesis, right? And based on that, comments. First, for large samples, we may use asymptotic results and use z-table to look up p-values, right? Because larger samples, the normality approximation is close. Using a normal distribution to approximate those samples makes sense. And also large samples, it's not easy to calculate exact p-value. So we use z-table. And second comment, we have some large observations in our sample, right? Which seem outliers, which make us wonder if our symmetric assumption is wrong. But since we use median to test the location instead of mean, you know that median is robust to outliers. Therefore, even with outliers, the test result should be okay. It's robust to the outliers. And regarding computational aspects, this course we will mainly use R, but stat exact is supplementary too when packages in R do not work well. But we skip introducing the details of the software packages. In next video, we will talk more about the packages and software and go through homework 1.